Hi guys, welcome to my YouTube channel. Today I wanted to discuss for the last session on the hybrid resonances. The previous video I was kind of doing the N3 minus with the structure like this, and we were going to do ORFC. So with ORFC, this means this guy have to be positive and this one being double negative, because it was it was like and negative. This is the Lewis structure. It has one negative charge. When we put one more negative charge on where the tip of the arrow was, we get double negative. So what we can do is that we can try to go on and move both of these charges one by one to the place where we get both of these charges on the other end of the molecule. So if one of them goes here and broke one of these bonds and put it on this nitrogen, it would then be and negative and plus and negative. We could also try to repeat the process with doing another charge and removing this bond. It would still be n positive and double negative. Now if we try to move back these two negative charge to the other place, we will go back to the first structure that we just got. So that's the overall resonance forms, and then we could do the hybrid resonance. That is the framework. The middle nitrogen is always positive, so I don't need to worry about that. Or you could say positive, positive, positive plus 3 over the 3 resonance forms, it will still be positive. Let's look at this nitrogen, the one on the end. That would be the same story for the other one. -2 -1, it would be -3, and 0, it would still be -3. Divided by 3, it would be -1. The same exact story for this one. So minus, minus, positive, plus, and then for the partiality, it's between a single and a double and a triple. So anytime you look at it, it would be still a single bond for the connectivity. Sometimes it's a double, sometimes it's a triple bond. So that's how the molecule is. That's the resonance, hybrid resonance for the azide ion, or N3 minus. Okay, now if you look at the charge also, it would be -1, the overall charge, and each of those resonance form would also have overall -1, -1 plus -2 plus 1, it would be -1. Also here, these two will cancel, and -1, the same exact story for the one on the top. Let's move on to an example where we could get a more complex molecule. Let's talk about the phenoxide with O negative and a benzene ring. Well, the first thing that I do is that I try to rotate the bonds in the benzene ring itself. So that's a second resonance form. It would be a double bond here. This would make a double bond. Oh, my bad. A double bond here, and this guy would also make a double bond here. So that would be the other resonance form, or you could try to do distribute the negative charge into the ring. So if it comes here and opens the bond and put it on that corner, that would make a double bond on the top, and oxygen would be chargeless. The two electrons could move to this carbon, making that a -1. Negative charge on this carbon could still move on and come to this place, so you could have another fourth resonance form with the negative charge on this terminal carbon, while this becomes a double bond, or it could still move one more time, putting the negative charge on this one, giving you a third resonance form, while here it's now going to be a double bond. So if you look overall, you could see that if this is the ring and that is the negative charge, from where the negative charge is, every alternate atom could be co-equally negative in all these 5 forms. Okay, so in all these actually forms that we could see, this one here happens to have 2 forms because the alternating bond could as well turn in the ring, not allowing that charge to move. Okay, so this is all the 5 resonance forms. Again, you could check it before you draw it. Every alternate atom, when you have a benzene ring and a charge is being distributed over it, you could actually see it as this sort of thing. So negative, this one is not going to be negative, but 2 adjacent are going to be. Also every alternate, so not this one, but this one could be negative. So you could see that there's a connectivity sort of. Let's go on. Also, this is important when we do hybrid resonance, so I would still like to have a little extra demonstration of where the charge could possibly go. On the hybrid resonance, these are the atoms that must have partial charging. This atom, if you look, this carbon is not going to bear any charge. So when I do the hybrid resonance, I do the connectivities, and there I know that this one, also these 2 are not going to have charges, but these 3 atoms and also the oxygen are going to have charges. These 3 would be exactly the same. Oxygen would be, because it's a different atom, it would have another charge. Let's just look at these carbon and expand it to the other 3. So if we just focus on this, no charge, no charge, no charge, no charge, -1. So it would be -1/5, also -1/5 for this, and -1/5 for this. For the oxygen, -1, -1, so it's -2, -2, -2, -2. So still it remains -2 because the other 3 it's 0. So -2/5. And then the partial bonding, like literally for every bond that you could see, it's between a single and a double. That's for this CO bond, and also for the CCs, single here, single here, single here, single here, double here. So it's between a single and double. And there you go, that's the case for all the other bonds in the carbon, and that's the final resonance, hybrid resonance. And if you look at this final hybrid resonance, the overall charge is -1, -1, -1, so -3, -2, -5/5, so it's -1. And the overall charge of the phenoxide molecule is actually, my bad, -1 from the very beginning. Okay, so that's how it is. Let's now move to yet another example. I'm going to move to a little bit harder example where you have a benzene ring and we could see how it changes. Okay, let me just use this to do this molecule. And a positive charge here. Now let me use my rule to see how it goes. The first resonance form that I could do is to rotate the double bonds, and that would give me just a plus sign, which still remains there. Those that are used to be single becomes double, and those that used to be double becomes all single. O negative. Now I could move that charge possibly, and if I move it, you could see that if it comes down, open up this bond, this location can be, so it's an alternate location. This is also one of them, this is also one of them. So that would be 3 more resonance form which have that negative charge in them. Okay, let's just do those 4. Actually, it's three more because one of them is with the oxygen itself, okay? So in all of them, this negative charge comes here and it becomes a double bond. For the first one, the double bond here will be gone as a negative charge here, and the two other double bonds remain intact. For this other form, a positive charge. For this other form, it could still move the negative charge to this place and open up the negative charge into this carbon, which is the other alternate carbon. Negative charge, positive charge, and this. It could still move to this place and open up the negative charge on this. So it would be a negative charge on this, a double bond, and then that double bond would also remain. Also, if you look at this resonance form, the negative charge could all the way through move and satisfy this by doing a double bond. So that's also one of the resonance forms, okay? So let's look at the molecule overall and say we have fixed resonance form, and the hybrid resonance would then be okay. Now if we look at our oxygen, -1, -2, -2 steel, -2 steel, -2 steel, -2 steel, -2/6. So we're actually 1/3. Let's do -2/6 so that we could figure out what we do. Here down below, plus 5/6. Only in this one there's no charge. And for these three locations where you have charged carbon sometimes, it's 0. It's going to be the same for all the other two, but we just focus on this one. So 0, 0, 0, -1, -1 steel, -1 steel, because there's 0 and 0 over these two in the bottom for this location, okay? So that steel remains -1, so -1/6. And if you look, the overall charge will now be also this location would be -1/6 and -1/6. The overall charge would be these 3 plus that 2 -5/6 plus 5/6, and it would be 0. Okay, so that's how this works for this molecule. The partiality, only these two bonds are the ones that remain single throughout. This go between single and double, also single, 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 single here, and just double here, so partial. For the benzene rings, we know that all of them go between single and double. It's single, single, and all double for this one here, so it's also between single and double. So that's the partial bonding, and that is our final resonance, hybrid resonance structure that represents all the 5 molecules that we're interested. Let's see if I do have more examples here to cover. Yes, I have an example which is interesting in itself. Naphthalene molecule is one of those molecules that I'm interested to talk about. Let's just go to naphthalene and talk about that for a little bit, as we have covered many of these Lewis resonance formed structures. Naphthalene is this. And I'm interested to know what happens when I move the charge. I will do it, and I'll show you a trick to come with the number of resonance form in a simpler form. So you could rotate these bonds in this in a circle in this ring only, and don't consider the other ring. That would give you this structure, while this part of the ring, this half of the ring remain intact, and you just rotate the bonds around that ring. Or you could also do the whole thing, like you do rotate the whole thing around this, or just this one. So any one you do, you just do the rotation on this ring, or you just do the rotation along the entire ring, like the two rings on this, you will end up with the second resonance form that would be this one. So a double bond here, a double bond here, a double bond here. If you just rotate this and this remain intact, or you do this and still you would got the same exact structure. So that's what you get. And now if you look, let me just get rid of these arrows and I'll let you know to show you the trick. If you look, this structure is just like telling yourself that there would be three possibilities. Let me just do red to show you how you do it. In any of these structures, if you look, there is alternate bonding. Okay, so a double bond and a single, and then a double, a single, and a double, and alternating in all of them. There is a point, where could I start? Okay, you could start from either of these three places. Okay, this one, or this one, and you would get a resonance form, and there's no more to go. Okay, if I do this and do alternate bonding, means these one are single, these ones are double, these are single, and these are double. This would be the exact same structure as this. Okay, so these are the same. For this one, you could see that you could do alternate bonding on this side and also alternate bonding on this side. And this is exactly the same as the one on the top. And for this one, alternate bonding, where these remain single, this becomes double, these remain single, these two become, my bad, double. Okay, and this is exactly this form. So you could kind of come with the third resonance form, and you could make sure that there is three resonance forms only. It's a little complicated on the count of the resonance form, though it's very easy to figure out what the hybrid resonance would be. And the hybrid resonance would just be two hexagons connected together and two circles in between. So that's Naphtalin's resonance form, and with that I hope that I could say I have essentially finished what I wanted to talk about in this video on resonance structure. I want to wrap up here, and I hope that you could actually do resonance form. It's basically the motion of charge where you have negative or lone pair. It uses conduits of double or triple bonds, and it actually goes to places where you have a neutral atom or a positive charge. And that is the very basic of resonance forms. Let's wrap it up for this video now.